So next I wanted to go over some thing that you might run into while you're working with vectors that you might want to do. So let's say you had vector A and vector B, and you wanted to know if vector A was going in the same direction as vector B. So the way that we would figure that out is we need to get the dot product. So how would we get that? So to start, let's import Maya, open Maya commands, or Maya open Maya's OM, then import the Maya commands. And then I'm going to get the world space position of A, and get the world space position of B. And then here I'm just saying I'm going to create an M vector and give it the world space position of A. And then I'm making an M vector with world space position of B. Now the next thing I need to do before I get the dot product, I need to get the unit vector of A and the unit vector of B. The unit vector is essentially just a vector that has a length of 1. And to get that, we just need to take the length of the vector and divide it by itself. So if the length of the vector B was 10, we would divide 10 by that vector. I'll show you that right here. So let's say AU for A unit vector. And we'll say A dot X divided by A dot length, comma, then A dot Y divided by A dot length, comma, then A dot Z divided by A dot length. And what that gives us, I forgot to put the parens at the end of these two lengths. And so that gives us AU, which is 0, 1, 0. So even though A is 0.2.075, 0, that still gives us 0, 1, 0. And the same thing goes for B. We go over to switch this to BU, BX, B length, BY, B length, BZ, and B length. We also get 0, 1, 0, even though this is 0.4.732, So now we have two unit vectors. Next we want to get the dot product. So actually before I'll jump to that, I'll also say an easier way to get the unit vector is to say AU equals A dot normal, paren, then BU equals B dot normal, paren. So this is what I would normally do, and it's much easier than dividing it by its length, the vector by its length. But I just wanted to show you what normal actually does. So now that we have AU normalized and BU normalized, to get the dot product, we would say A, so I'll do paren AU dot X times BU dot X, so then plus AU dot Y times BU dot Y plus AU dot Z times BU dot Z, which gives us the result of 1, because these vectors are both going the same direction. Now the Y of how this works is a little bit, somebody figured out that if you multiply two vectors by each other and add them together, it ends up giving you this useful result. If you were to not normalize, let's say I just took A and B, you still get a value of sorts, but that value is a little bit less useful. So if you look at the dot product, it would be 9.817. So there's a good reason for using a normalized vector. And it's not just one that we can test for. So if we go and move A in the opposite direction, and then we test our code again, throw out this because we are getting the normalized vector here now. We get -1 because this vector is going from 0 to A, which is the opposite direction of 0 to B. If I were to move A up here and then just off to the side a little bit, that would end up giving us 0.67798 and so forth. And then if we want to even do this math even a little bit easier, rather than getting the dot product this way, there's a built-in way. So we could say dot equals A dot normal times B dot normal. And the reason this works is first you have your A vector up here. Then we have A normal, which gives us a normalized vector. And we have the B, which gives us our normalized vector. And when two M vectors are multiplied together, it is assumed that you're trying to get the dot product. So it just returns the dot product. So if I were to snap this back on, return the dot product again, we would get, well, I didn't retrieve the new vectors. So we get the new dot product, and it is 1. So that's how we test vectors against other vectors.